Okay, so we're going to.
So there's one data set, and that's right.
Yeah. Here's our drive. So several different ways you can go about it. You can do data search, and then we can go zoning. Oh no, that's showing up. So we go council planning tribe. Yeah, so no. All right. Go in data sets.
Yeah.
Go down under land management.
Okay. Boundaries.
Yeah. No, under property and planning. Drop property and planning down, and then scroll down land development plan zone categories.
What's the blue one mean?
The blue one next to that, I think that's Randall C historic zoning. Let's have a look at that. Yeah, historic conservation, Randall C. So there's yeah. There's a lot of a spattering of old limestone buildings through that section there. Yeah. Yeah. All right. Yep. More questions in regards to the assignment? You're done.
Yeah, I'm pretty lost on how to like get the information down in the way you need it. Like, there's a lot of stuff like maybe the health and safety or the roof and stuff. Not too sure what you want for that.
Well, for many aspects, there's not going to be anything specific about health and safety. So yeah, there are very different things. So yeah, typically working with your standard timber frames, no issue. With things like hardwoods, cutting hardwoods and whatnot, it is important to wear breathing apparatus, well, sort of mask at least, because continued exposure to a lot of your hardwood dust is really bad for your lungs, and there's cancer associated with that.
More with the construction of it.
Yes, more in the construction of it. Yeah, there certainly, if you were going to specify things like a loop bond and whatever for, or flammable claddings, things like that, then you're going to say, okay, well then there's health and safety concerns with that. So for most of it, it's not going to. For most of these things, that's not going to be applicable. But yeah, but for some products, it is. So it's about identifying that where you can. And you may and so you may find that with many of these categories, you go, it is not a significant concern for this technology.
And with your references to Australian standards and stuff, like if you're doing a truss roof, do you want to spell out how to do the whole thing?
No. So it's about going. Timber frame trusses have to be installed as per AS440, and you can specify important aspects of that, but yeah.
Actually go through and do it.
No, don't pour through. Yeah, and say too much. Yeah, because if you start summarising Australian standards, you'll still be here next semester on the first assignment.
And this week.
Oh, that was USB.
Right. Okay. Yeah. All right. Yeah, I'll take that. I'll drop that down to security when they take over this. Yeah.
This week you wanted to see the OneDrive.
Yes. Yeah.
So how do you send that?
Okay. All right. Let's have a look at that. I haven't shared mine with anyone yet, but from what I understand, it's fairly straightforward process. So have a look at OneDrive.
Oh, OneNote.
Oh, sorry. Yeah, OneNote. Yeah. Yep. Thanks. So yeah, OneNote. So here we go, and up the top here, share. So I'll see if I can. There we go. So I can share it with you. Yeah. So that should be. Yeah. I probably don't want me to share mine with you because there's really nothing there. But yeah, start typing my email in there, and it should pop up as a contact through the tape. Yeah. Have a, I'd say type in add another as well, because I saw there were several options there, and yeah, Mark Jenkins is actually a relatively common name. Just making sure it's going to the right one. So have a look for, so type it in again, Michael Jenkins there, and space, and then JENKIS, and you'll see the box drop down. Yep. So you've got, yeah, these are my students. Okay, that'll be me as a lecturer then. Yep, that's fine. Go with that. Cool. That's it. Yeah. So yeah, and that makes sense for everybody else there. The sharing of the OneNote. Fairly simple. All right. So yeah. So what we're doing is bring up the OneNote, and top right hand side here, you've got this purple button that enables the sharing. So that's this here. Click on that, and then type in my name, and I'll pop up. So type in Michael Jenkins, and I'll pop up there as the first choice in your list to share with, using a TAFE OneNote, and you can share it with me. Okay, and yeah, more questions in regards to the assignment, or things to be clarified. Or if you want me to touch on some things to get you going as well on certain aspects, I'm more than happy to deviate from from the lecture plan as set out week by week. Nothing else?
No, some of these points, so maintenance requirements, is that just basically upkeep, how long it's going to last?
Yes, exactly. Like so what do we do? So typically a lot of your maintenance for your framing is not important. Certainly if you've got all your weatherproofing details correct. However, you've probably noticed that on almost any house of a decent age, that fascias, etc., that's your first entry point of rot. Typically these days we use, well, not typically, probably exclusively, we should use H3 LOSP treated timber for fascias. So it's suitable for that application. But still, it's important to keep paint up to fascias. And also, any timber you can get H3 LOSP treated, but it gets cut on the ends. That's an entry point for attack and for sort of decay, etc. So typically that's your only sort of real weak point and real area of maintenance required for timber frames, unless you've got timber elements exposed. Maintenance in regards to, they think of other building products. Well, typically there's not a
Steel.
steel. Well, yeah, once again, steel needs to have protection against corrosion. So galvanizing typically means that the steel will last a very long time without having any maintenance requirements. But if it is unpainted steel, well then, yeah, or if it's ungalvanized and it's painted, then yeah, that needs to have paint applied. regularly to keep it in good condition. Roofs, so roofs typically have a lifespan. Your sheet roofs are fairly free of maintenance. Your tile roofs require more maintenance. So your mortar on your ridge capping, hip capping, etc. That needs to be done fairly regularly. And you get mould, so lichens growing on your roof as well with tile roofs and collection of moisture, etc. So typically tile roofs require a fair bit more maintenance. Other maintenance aspects in relation to housing. Um, you must, I think the most important maintenance aspect in regards to housing is ensuring that gutters, downpipes, etc. are not leaking and not cracked at the ground level. That's probably the biggest issue for housing, to ensure that there's no moisture where you don't want moisture. Yep.
Compatibility in conjunction with other elements, is that just to discuss steel, concrete?
Predominantly yes. Yeah.
Glass?
Yep, exactly. So, but you might also talk about things like if you've got a very lightweight frame building with large openings, lightweight frame buildings do tend to have a lot of flexibility. That, in conjunction with large glazed components, you can have pressures acting on windows, etc., breaking glass. That's also, I think, a compatibility consideration. And you've got to use rigid portal frames around um, large openings to provide that bracing and that rigidity as well. You could talk about the weights of say, cladding forms and so on, and its impact upon footings, etc. That we're not going to use a suspended timber floor on stumps with with double brick cladding walls, for example. If we're going for a lightweight flooring system, we're going to have a lightweight building above it. So some of our heavier cladding and construction approaches are not going to be suitable for lighter weight footing systems. But certainly, so we could talk about it in regards to differential metals. So, metals which are more reactive than other metals. We don't want them interacting together. We certainly need to ensure that paints are compatible. That we're not doing an acrylic over top of an oil-based paint, for example, or there are certain paint finishes that are even oil-based paints which are not compatible with other paints and other coatings, etc. Or floor ceiling systems are not compatible with certain membranes, so waterproof membranes. So yeah, you can make a note just that any coatings applied have to be compatible with any future coatings or also in that regard. Is that fairly well?
Just one more thing.
Yeah,
about,
sure.
roof cladding and stuff. How are you going to find out the information about thermal properties?
Well, in regards to how that roof will perform in a thermal sense, well, within one of the I guess one of the aspects you can look at straight away is within the National Construction Code. If you look at your climate zones, let's say we're doing in climate zone 5. If you have a dark roof, then you have to have like a dark coloured roof. You have to have I'm not sure exactly the figure, but insulation of R5.5, and then if you have a light coloured roof, then it's down to 5.1. So the National Construction Code differentiates between colours of roof and its thermal properties in that regard, and what form of insulation you need. But also you can look at your different types of roof cladding and tiles as compared to sheet roofing as well. So sheet roofing gives off a lot more radiant heat underneath than a tile roof will give off. Because the transmittance of temperature through steel is much higher. The conductivity of steel is much greater than terracotta or concrete. Any other aspects to have a look at?
Yeah, I think pretty good at just being able to actually look up to them both with all the different parts.
Yeah, yeah, yeah.
Yeah, I haven't got that far, honestly.
Yeah, and probably the best way to do it is, you know, just lots of small bites from many different perspectives as well, that you can go through and go, all right, well, this is all the easy stuff. This is all the stuff I know. I'm ticking off these boxes. These ones I haven't ticked off yet. I'll find out about those, and yeah, and that way it sort of narrows it down. It makes the task a little bit smaller when you've been able to hammer out. Okay, these are all the things I can answer.
So if you're getting
Well,
stuff from like some architectural site, and
yes.
they've got different kind of other standards, like let's
Right. In terms like American standards.
No, European standards.
European standards. So it's best not to draw any comparison. Certainly, yeah, certainly. How to say it? The use of products has to happen somewhere, and you know, by and large, it's happening in Europe or the States until it gets adopted here. But the thing is, we should not go specifying any products which haven't had Australian certification yet, because there's a world of issues in regards to that. If you were going, oh well, look, this glazing system is going to have Australian certification soon. They're in the process of doing that. Let's specify it, get it happening. It gets built, goes in, and then they don't end up getting certification for it. Well, then your options are to, you know, either remove that or where that liability. So yeah.
So an Australian company has decided that.
Mm-hmm. Yeah, it's an Australian company, but what some of the products they have don't have Australian standards.
Yeah, well, it doesn't say that. It just says data sheets.
Yeah. Yeah. If it's, I think for the sake of this assignment, it's probably
Steer away from it.
yeah, steer away from it. Go with what's easy. But for, you know, for really cool stuff, if it's worth exploring, it's worth exploring later on. Put it in your OneNote. Be aware of it. If you've got spare time, chase up stuff. Contact the suppliers as well and say, look, I'm very interested in your product. Just wanting to know some of these things, just for your own sake, but for the sake of the assignment. Um, I guess go with information sources that are going to be much easier to find. More questions in regards to that, specific things on materials. So we've got those ideas for floor structure. Everybody has plenty of ideas for wall structure. Yeah.
If there's multiple cladding across, because you're talking about the building that they're doing.
Yes.
If there's multiple different claddings or wall structures on the building, so one side's using Hebel and the other side's using something.
Standing seam.
Yeah.
So, yeah.
Do you talk about it in the briefing or?
No. So simply we're talking about, so we're not, I guess there's not a great deal of direct reference to the building as such. So this is a building and this is supplied so you can imagine a building basically. And then what sort of materials can you use on a building of that nature, and just talk about that. I guess if you're wanting to find some things to talk about compatibility and interaction between elements, you can say, you know, if we were to go with a cladding system that is, you know, part brick veneer, part this, etc. We've got to have control joints. We've got to think about differential weight on the footing system, all that sort of thing, if you wish. But you can also just make it very simple for yourself and be specific to those techniques. concrete, because following this, there's going to be a very similar assignment but based on a multi-residential building. So that's going to allow you to look at some other forms of construction. So I suggest keep it really simple, really basic for the residential, because you get to explore other stuff for the multi-residential, and then it goes on to a 3-story commercial premise. So once again, you get to explore other options for that. So yeah, keep it as simple as you wish for the dwelling. Yeah. So last week we covered predominantly timber framing, touched a little bit on light gauge steel framing as well, and we'll touch again on light gauge steel framing further on, because that's also an important aspect of commercial construction. I don't know what these walls are constructed of, but I would hazard a guess that it's rondo steel framing in behind that they wouldn't have used timber. So that is sort of the mainstay of a lot of your non-load bearing walls in commercial construction. Although that sounds like a very rigid plasterboard, that one. It's a bit more than your standard sort of residential plasterboard. I wouldn't be surprised if that was a 13mm or impact check or something like that to give extra strength for mounting these boards and so on. So what we'll be looking at today is concrete, and concrete's been in the news a bit recently. Now, unfortunately, I've just been flat out with doing a lot of TAFE stuff and haven't been able to really keep up with the news and the news around this bridge. Anybody able to enlighten me if there's been any determination? So the big bun fight, whether stuff has landed on anybody particularly, or so in regards to that.
There's a couple hundred people dead.
Yeah.
It was the engineer's fault.
Right, it was.
It was
yeah.
all to do with the structural integrity of it.
Yeah, so the initial design or the fabrication of it, or
initial design.
The initial design, yeah.
Caused too much vibrations.
Right. Yeah. Yeah.
My dad's an engineer, told me.
Yeah. Great. Yeah. So there's just too much flexibility in there, transferring stresses and causing failures. Cheap materials as well. Yeah. 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 So from that, okay, obviously the engineering design aspect highly important. The material specification aspect of that highly important. Now I don't expect. Now certainly some of you may go work for engineers and work on projects like this. Be doing drafting work, etc. I certainly don't expect you to be designing like pre-tensioned bridge beams and so on for doing that and specifying the concrete, but certainly be aware of the importance of that and how important it is to understand materials. But having talked about the Grenfell Tower previously, that is the sort of thing that you will, it's highly likely you'll be involved in things like that, in drafting and the specification of materials like that. So that's very important. So I take it from that, probably Christian, you know a bit about concrete. Then do you? No.
I hear my retired old man ramble on about.
Yeah. All right. So, well, yeah. If there's any pearls of wisdom that drop out during the lecture, by all means let me know. But if we're talking about floor structure, predominantly in South Australia, we're talking about a raft slab, concrete. That's you walk out of here and look at any residential building on your way out of here. So 99% chance it's going to be sitting on a raft slab. Certainly we deviate away from raft slabs when we're doing cheaper builds. So where it's going to be like beach house, river shack, all these sort of things where people don't want to invest as much money in those. Well then, yeah, we go for lighter weight structures. Also, we can go for lighter weight footing systems, structural systems, when we are on more stable sites. So a lot of the soil in Adelaide is just really reactive. There's a great deal of movement that happens here, and your lightweight, like your steel flooring systems, your timber flooring systems, just don't handle that very well. certainly there's technology in regards to adjustable piers and things now that can be adjusted, but still that requires that ongoing maintenance of those systems in an adjustable or in a reactive soil situation. And there are recommendations around about whether you can, what sort of soil reactivity is appropriate for various different flooring systems. So raft slab construction. That's footings are by no means new, and concrete footings are by no means new. The Romans have been doing it for a very long time. A lot of places throughout Europe, you probably can't walk around without stumbling over a Roman ruin too far. Very broad empire, but they left an architecture or footing system that's lasted for a very long time. But the raft slab is a fairly new take on that. You don't have to, and I guess it can be fairly interesting to look at buildings through time in a place like Adelaide. We'll look at a building built today, sits on a raft slab. Look at a building built in the 1960s or so. We were talking about strip footings with brick plinths and suspended timber floors. Wind the clock back further to about 1920. We're talking about strip footings that are a combination of concrete and bluestone, things like that. Wind it back further, 1860 or so, it was large bluestone slabs with built elements over it. So not a very long timeline. We can see a very big progression in footing systems in a place like Adelaide. But predominantly, it's going to be raft slab footings. So none of us are going to be designing raft slab footings. I'm not going to be designing raft slab footings. I'm going to have a general idea about what's going to be specified, and I'll make plans accordingly. I'll be thinking, okay, in this particular site we're going to have beam spacings at around that 2 meters. It's probably going to be 600 deep, 300 wide, etc. Think about that's probably what the engineer is going to specify. But what I'm not going to do is I'm not going to specify that footing system. I'll send that to an engineer for them to determine what size, what thickness of slab, what strength of concrete, what size of beams, what size of steel goes into reinforcing our slab. So they're going to compile the footing report, and they're going to want to carry out inspection of the trenches and the footing steel. The reason for that is, well, they want to ensure that that slab is built and constructed as per their designs. They want to know that the right amount of steel has gone into that footing system. Steel is expensive. Some builders may want to cheap out on the steel. So engineers have to ensure that goes in, because once a slab is down, once the slab is cast, you can't really be digging it up and having a look in there and go, oh no, these are N12 bars instead of N16, unless it's a bridge and it falls down, and then somebody can make that determination. But typically that's not going to happen. And also they're going to want to know that those trenches are formed correctly, because if the trenches are formed in a bit of a wonky fashion, it's going to impact on the strength of those footings, but it's also going to impact upon the amount of concrete that's required as well. You're going to have to order extra concrete. And also with all of our footing systems, the location of the steel is important both for strength and longevity. If the steel is too close to the outside of that concrete, it can be subject to moisture and it can rust. What happens when steel rusts is it expands. And when it expands, it pushes concrete out, which makes cracking in concrete, which makes that steel rust even faster, which cracks it even faster, and you get footing failure as a result. At that same time, you may want to get your structural engineer to do some other calculations as well, be that some roof truss design or retaining wall design. So any retaining walls over 1 metre have to be designed by a structural engineer as well. Now, not all structural engineers will touch footings because there's a lot of liability tied up with that. If footings are done wrong, it's not something that can easily be rectified. And so not all engineers will have the insurance for specifying footings. And typically, a lot of your trusses are going to be designed by truss manufacturers through the engineering software associated with that. Engineers will establish the worst case scenario and design the building elements to resist that loading. In terms of loads, we've got several different types of loads. We've got dead loads and live loads, wind loads. That's typically what we're dealing with. And I think we made that observation previously in regards to timber frames, that it's best to be conservative in regards to your tie downs of timber frames because it happens. It happens. Roofs and so on get ripped off, and incredibly expensive thing to go repairing and to rectify and reinstate. So your dead loads and live loads, within this room here, we don't have a huge amount of dead load. Dead loads are anything that's sort of built into the building that we will expect that load is always going to be there. So yeah, really in this building, maybe these pin-up boards, you'd say that's a dead load. There's not a lot of load in that, but beyond that, not a great deal. All of these desks are transportable. That relates to the occupancy of the building, how the building is going to be used. Half an hour ago, there was, less, there weren't any people in this room. There was less weight on the floor. Now there's more weight on the floor, and we can have a small class like this, a very small amount of additional weight. We can have a very large class, have 5-6 times the weight imposed from a live load. So anything to do with the use of the building, and you have to design to that worst case scenario. So possibly we're going to have a cocktail party in here, people are crammed in, and someone's going to be playing a grand piano in the corner or something. So it has to be designed for those worst case scenarios. Wind loads. Wind is doing two things. It's lifting a building up. As it pours over the building, it creates uplift. It sucks on that building, trying to take the roof off of it. It also pushes on the side of the building, trying to elongate that building and push it over. So I've got the building over here. Get this one happening in here. So we've got a bit of bracing on there. Now obviously that's not going to really do any not going to be any chop. It's bracing, it's a piece of plastic strap, and it's untensioned. It's very important that bracing is actually tensioned up, because if bracing, and so I think I mentioned that previously. We've got a new fire station out where I live. One of the first things I noticed in there, the bracing sags in the roof. There's big sags in the bracing. So that bracing is not active, and it's not going to become active until there's a lot of deflection happening on that building. There's going to be, that building's going to be, partially twisted before that bracing is activated. So bracing in your frame does need to be very taut. So you install it by, stretching around, pulling it with the claw hammer, stretching it, nailing it off with the other hammer or your nail gun, whatever, and then you put tension that's in your bracing to tension that up, to provide tension there, so that when the air or when the wind pushes on the side of the building, a pushing force in this fashion, this piece of bracing becomes activated. A pushing force in this direction, this piece of bracing becomes activated as the wind tries to elongate that rectangle in that fashion. So you've got strap bracing like this. We don't have any sheet bracing on this, but it's fairly simple to understand. Piece of sheet bracing, OSB board nailed on there. Sometimes you can increase your kilonewtons of bracing by including rods going from top to bottom, tying the top plate into the floor structure to provide that extra vertical restraint that works in concert with that sheet bracing as well. So your standard sheet bracing has about 3 kilonewtons of restraint per linear metre, you can increase that to about 6 kilonewtons per linear metre by having rods going through. So that's what wind is doing on the building. It's trying to elongate it, and our bracing reacts to that. We also have other ways of looking at force as well, beyond just our load. So beyond just our loads. So I've talked to you about compressive force and tensile force previously. All right? Yeah. Everybody's fine with that. I won't keep going on. One thing I probably didn't talk about is shear force. That's where you've got two almost directly opposing forces, but with a slight amount of eccentricity. So when you've got two forces opposing each other directly, then that's a very, very compressive force. But if I add some eccentricity to that, so they're only just slightly offset, it becomes a shear force. That's where you get, cracking of building elements in a vertical or horizontal fashion. Typically, our forces are seen through deflection. Now, building, from a structural perspective, everything's going to deflect to a certain extent. Even concrete will deflect to a certain extent. You get high-rise buildings, the amount of weight in a high-rise building, it needs to be catered for that building is going to compress slightly. We don't often think about high-rise buildings as being these things that compress, or as concrete columns as being things that compress, but they do compress. Everything compresses slightly, and also everything deflects slightly. Now, what we want is for that deflection either to be hidden or to be non-perceptible. So these desks, for example, there'd be some deflection happening in that desk, but the desk fabric is so rigid for its span or its cantilever that we can't see that deflection. If I lean on here, then you can see that deflection. So, but even in its state like that, just with gravity acting upon it, there's going to be some minute amount of deflection. What we want is for that to be imperceptible. We also want to ensure that we don't have deflection which causes loads on other building elements that weren't designed to have loads. A really good example of that is to look at the windows here. Now, certainly there's going to be some deflection in that concrete slab up above, so we have to have an area above those windows which is compressible to ensure that any deflection that happens in that slab, in millimetres, isn't going to be transferred onto those windows. Now, those windows, that glass is sitting, for those ones there, it's sitting in a rubber bead. There is some flexibility there, but what would be a very bad scenario is if there was no space for deflection at the top, very rigid fixing of glass in there, load was transferred to the glass broke and fell on students down beneath. We have to allow for some deflection. We have to think about deflection and ensure that it doesn't pass loads onto elements that are not designed for taking any of those loads. But also, we want to, sometimes we're going to have elements that will deflect, and we have to hide them away in the building as well. So that's things like lintels and so on in wall frames. So your lintels, these are the lintels happening up here, that above our windows there. Those lintels are going to deflect to a degree, but that lintel is going to be hidden away in that wall frame. You're going to have that little bit of deflection, but you're not going to see it. Also, within your roof, you're going to have deflection of particularly pitching beams, where you've got a major beam, a strutting beam. You've got a major beam in your roof that's helping to strut up a roof that's taking a lot of load. That's going to deflect, but no one's ever going to see it because it's hidden in the roof. Another important aspect to think about when we're thinking about deflection is the deflection of roof trusses as well. And I'll just quickly talk about that. With your standard pitched roof, so this is a pitched roof where we've got rafters, underpurlins, etc., all these elements working together to hold those rafters up. With your trussed roof, your trusses work as a single structural unit in and of themselves. So So these webs in here between our top and bottom chords help spread the load between all these bits. So if I put weight on here, that is expressed in other areas throughout the truss. It's a single structural unit. But when I put a load on this truss, there is going to be some deflection of the bottom chord. So if the bottom chord is going to be doing this, we have to design our interaction of the trusses with that on our roof in accordance with we have to think about how they interact with our internal wall frames. Inside a building, if we were to use trusses on this building like this, then none of those walls on the inside of the building would be load bearing. The only load bearing walls would be this front wall and the back wall. Possibly there'd be some load from these hip ends as well if we're doing what they're each going to be with a hip roof. With a gable end roof, there's going to be no load on or imperceptible load on those ends. All these other walls are non-load bearing, but if we're going to have bottom chords that deflect, and we're going to be fixing non-load bearing walls to those bottom chords inside the building, we need to have some accommodation for movement happening there as well. And the way that happens is that's a cross section of our bottom chord. In fact, I'll get another pen. That one's about cactus. So this is our bottom chord of our truss. Oh, that one's not a great deal better either. All right, I'll just push on. Right, so that's going up and down. So there's some movement happening with that. This is the top plate of our internal wall frame. That's our stud going under that. So we have a small amount of space between those. In fact, actually, what I should have done is I'll draw the wall heading this way. I'll do it perpendicular, so we're not cut through like that. So our top plate's running this way. Our truss is doing that. So we fix our top plate there to our truss, but if we look at that in elevation, this is our fixing plate, our L-shaped fixing plate there. We have elongated nail holes like that. So this plate is nailed straight through there, but it can move slightly. And then with our cornices, we ensure that so we've got our gyprock ceiling lining there like that, or whatever sheeting product we've got. Got our wall lining there. Those two things have a slight gap between them, so that this one can go up and down. We're just talking about a few millimetres. But in a storm, we've got a few millimetres movement up and down. And then we fix the cornice to the top one only. And we leave that side abutting the wall, but not fixed. So that cornice can go up and down slightly as well. Because if we fix the cornice to both sides like that, and we get trusses moving up and down slightly, that will break and it will tear off a bit of plasterboard and whatnot and look terrible. If you at least paint to the underside of that and you get that millimetre or so of movement, you won't see it. So building elements deflect, and we have to design to cater for that. There's a bit of, I guess, sometimes you get people talking about footings and foundations and sort of mixing them up. It's not too rare to hear someone saying, "Oh, my foundations need underpinning," or something like that. You know, they'll say, "Oh, my foundations are cracking." Well, the foundation is actually the soil or the site that you build upon. What goes underneath your footings. Those foundations can be improved. So it's about the natural soil, but that you can improve your foundation by bringing in fill and compacting that fill. But it's the soil or the earth that you end up building upon, which is your foundation. Your footing is your lowest structural element. So typically your footing in Adelaide is going to be a raft slab. construction, but your footings may also be concrete piers or concrete pads or screw piles or something, whatever it is that interacts with the ground to transfer the loads of the building into the ground, and also to tie the building down to the ground. I'm not sure if I made mention of that last week also, in regards to uplift forces as wind pours across buildings, trying to rip buildings up. I'll bring the house out for that. We've got wind pouring over this house, trying to rip this roof off, but we've tied that roof down adequately to our wall frames. So the wind just keeps pulling on that, it's trying to rip the roof off and trying to rip the wall frames away. Our wall frames are tied down to our floor frame. Try to rip the whole thing away, that's tied down adequately to our stumps, which is tied down adequately to concrete footings. Or in the case of most houses, this is going to be a concrete slab. We tie our wall frames down to the concrete slab. That's going to happen through masonry anchors, and it depends on the kilonewtons of restraint that those masonry anchors are designed for as to how many masonry anchors we need in our bottom plate. So that's going to happen in a way that we have our footings here, that, and then our bottom plate on top of our concrete raft slab, and then we'll have a masonry anchor down into that concrete slab, locking our bottom plate in there. And we'll probably do that hoop strap tie down 35.8 gal strap underneath our bottom plate like that, and nailed to our studs. Like that to tie it all down. In terms of those masonry anchors, we also, whenever we have bracing like this, well, any form of bracing, but this strap bracing here we've got on there, where we've got strap bracing tied down to our bottom plate, we need to have a fixing of that bottom plate straight into the floor slab at that point as well, or within 150 millimeters, because as there's tension put on that, it's trying to pull that bottom plate away from our floor slab. So various different types of footings: integrated, raft slab, pier and beam, strip and beam, pads and piers. We won't go into that. Well, we'll go through all of those, because essentially what you can do after this. So we talked about suspended steel floors. We talked about suspended timber floors. Talked about concrete slabs. But you could say, all right, well, we'll do. I'll specify a raft slab. I'll specify a concrete pier and beam footing structure. I'll specify a strip and beam, and then you got 3 footing systems constructed of concrete as well. So many, I guess, a few structural options in here. So our structural options are going to be dictated by our soil profiles, about whether that soil is stable, reactive, soft, or collapsing. So the majority of Adelaide soils through the metro area, what are they? Clay. Yeah. So reactive. That's typically what we've got. So we deal a lot with this. In fact, what I'll do as well, I'll just bring one up. Bear with me just a sec. So. Going to open. Give us a good. Was going to be? Nah, it's going to be too small. I'll go to the next one. There we go. So soil map of Adelaide. So I don't know. Do any of you live on that page? No. So think about where you live. So yeah, there's some absolute shockers around here. These patches. Yeah, very reactive, very reactive soils in there. Typically through here, not too bad. You've got some problem sections through there as well, though, for other reasons, but generally your soils are fairly good. gonna scroll up a little bit. But also, strange enough, what you see is people who live in old cottages around here, so Unley Parkside area, you've just got massive amounts of movement, like cracking in all these walls, etc. But then further on down, getting out here, you've got buildings built in the 60s and the 70s which don't display any movement, sitting on exactly the same soil. The difference is footing technology that has changed. The buildings in here, Parkside, Unley, etc., were built on strip footings. You've got solid masonry walls, probably about 200 mil thick, on bluestone slab footings. That can't handle that sort of reactive soil. So there's movement and there's cracking, etc., and you've got walls sort of wandering away from buildings, and you've got tie rods happening through buildings and whatever to hold them all together. Whereas that footing technology has changed significantly. But also, strangely enough, what you get are things like this. So I used to live just in here. Now, I was just on that light green patch there. That is actually really good soil for building on. It's really quite stable. But you go just slightly further down the street, you know, 100 metres further down, and then you're into this stuff, the reactive clay. So the soil that you're building on can differ significantly, you know, within a street, also. Yeah, but these are your real problem areas. There, these bits, and also we've got similar sort of soil like that happening down Claren Vale and whatnot as well. So it typically goes with, you know, places that are great for growing. Yeah, not always so good for building on. I'll shrink that one down. Where's our other slides? So that's the majority of Adelaide's soils. We don't have a lot of the stable, what exhibits little movement and provides a stable base. But what we do have in areas, we have stone close to the surface. And stone can be a blessing in that regard because it is a stable base. We've got that stone to lock the buildings onto. We have some soft soils, so in places down near Port Adelaide, etc., there are some soft patches. They, you know, highly compressible, unable to support loads, so you've got various different deposited soils that have high humus content and whatever in them. And then you've also got collapsing soils. They're typically your sandy soils. The only collapsing soil I've had any involvement with was a building at Renmark that broke a downpipe. The water, a lot of water came out of that downpipe, saturated the ground there, lubricated all those sand particles. Those sand particles sat close together, removed the support for the building. So that's typically what collapsing soils, or what makes a collapsing soil collapsing, is that you've got these sand particles that sit together in a funny sort of fashion, but then you add water, they fit together in a better fashion, and then they shrink and don't support load. But one of the things you had happening in Christchurch with the earthquake there, a similar sort of thing, but no water involved. So you had shaking of the earth and sand particles sitting together better. And then that removed support for buildings as well. So you not only had the earthquake loads going on, but you had soils collapsing as a result of that vibration and that settling. So you need to have an idea about that soil. So you do some preliminary soil testing if you wish, or you go ahead and do a construction report. So you bought the place and you go, all right, let's get these footings designed. So construction report will detail the footing type, the site works, the bore log, the contour plan, cut and fill information, and paving advice. Anybody think of why paving advice is important? Yeah. I think it's more about stopping moisture getting to your footings, because in a reactive site, what you don't want is a lot of moisture right next to the building. In fact, what you don't want is moisture changes. You don't want it to be saturated, dry, saturated, dry. You want that moisture to be stable. So if you provide paving around your house, the water will run off, but it sort of locks some of that moisture underneath in a stable fashion. That's going to provide a lot of stability for your soil around the sort of foundation around your concrete footings. Cut and fill information is important. What would be one of the first things you look at? Well, a couple of things you look at for cut and fill information. Alright, so someone's given you a plan. You go, okay, this is where we're building the house. We've cut this bit out here. We've deposited soil here. What sort of things would you be thinking about? So what I would be thinking about is, do I have any retaining walls over 1 metre? Do they need to be engineered? Is there any way I can get away with having 2 separate stepped retaining walls that aren't 1 metre high? Things like that. So think about that. Or if we do have a huge cut, how are we going to do those retaining walls? Is that going to be a huge investment? This is a very sort of abnormal situation, but I was involved in doing drawings for reinstating a retaining wall in Springfield, so a very expensive part of Adelaide. I think the job ended up costing around $150,000 to do, for the reinstatement of this retaining wall that was failing. You had a building up high, a building down low, not a great deal of space in between them. This building was coming down, or threatening to come down toward the other one. Very important, that that's rectified. So certainly worth spending that sort of money on a scenario like that. But it's an incredible amount of money for walls, and so that has to be taken into consideration. What your retaining walls are going to be. But also with that, I'd be thinking about, okay, we've got this was our hill previously. We've got a cut and fill happening there. So this is our cut here, and this is our fill here. How consolidated is that fill? And are we going to, in doing our concrete raft slab, are we going to have piers underneath that end of our raft slab there to help support that? Because if we don't have piers under that, and then we have settlement of that soil over 5-6 years as it consolidates, then we get cracking through the slab right at that point there. So we'll want to know about that. We'll want to know about the depth of that fill as well, and whether it's whether that fill is the soil that was cut from there as well, and whether it was rock or not. Because if you've got sort of some more friable rock that's broken out and it's laid down, you've got a large excavator running around on top of that, compacting that as it's dumping more soil, you're going to get a lot of compaction. You're going to get a lot of a fairly solid base under that, as opposed to if it's a very sandy sort of soil that has been cut out and deposited there. You're not going to get a great deal of compaction. You're not going to get a great deal of strength underneath that. Contour plan, that's going to be important because it's going to dictate where water is going to be going. It's going to dictate what your footings are like. Christian noticed that the site nominated down at Finnisvale Drive there at Second Valley is a sloping site. How is that going to impact on the project things? What sort of things are you going to do in regards to that? So we'll talk about bore logs in a bit. And site works, so we want to understand what's happening with site works, etc.
Is it true that you don't need council approval for retaining walls more less than 1 metre?
Typically, it is true. Pretty much anything to do with councils, you've got to see it as being council specific. Now, certainly councils sing from the same hymn sheet a lot. That you've got these rules that are the same cross councils, but you should not. You should never assume. You should never go, all right, yeah, I can do a retaining wall less than 1 metre without council approval. Always check with your council, but typically that's the thing. So you can go onto your council websites and you'll see various different fact sheets, and there's typically going to be a fact sheet on retaining walls, and it will give you advice, probably similar to that. So bore logs, all that soil samples. That's a soil sample taken out of the ground. Now that's not typical for your residential architecture. Typically your soil sample is done on site, done with a hollow drill on the back of a Land Cruiser. They come out to be about this size, 30 mil or so out of maybe that one's called a push tube, I don't know, but it's a big stainless steel thing that gets turned and it gets pushed down into the ground to sample soil. Although I've also seen soil being sampled inside the hallway of a house. So floorboards up, two-stroke motor, rammer on top of these things, and then setting up a block and tackle and winching out the pipes directly and undoing them and tapping the soil out. So soil samples can be taken in all sorts of locations. Typically, though, it's going to be on the back of a four-wheel drive. Does that, and they're going to produce things like this, and that's going to sit in a core flute tray. And the engineer, this fella, he's going to have a look at that and look through the soil and see what the properties of that soil are. So he's going to have a look at that and go, okay, it's prismatic structure, it's got weathered rock particles, etc. It's high plasticity, low plasticity, clay, sand, all that sort of thing. So he's going to be looking at those things to determine how that soil is going to behave. Is it going to be collapsing? Is it going to be reactive, etc. What you're going to want to do on site? So typically your soil sampler. Well, so what we always did with the engineering office, what my job was a lot, was to produce site plans ready for the soil sampler to take out with them. So they can go measure where those borehole locations are, mark those on the plans, and they come back and I draw them up. That's going to look a lot like this. We've got your site plan and your borehole locations. Those boreholes typically marked like that. BH1, BH2, BH3, for example. You cluster them, aggregate them where your house is going to be. So let's say our house is going to be here like this. So in a city place, it's taking up the whole block. And then, because it's important to know where those soil samples are being taken, because soil horizons differ through those soil samples, as we'll see in a minute. From that information, taking that soil, the engineer is going to look at that soil and work out how reactive that site is going to be, or how reactive that clay is, and then they're going to give it a determination whether it's stable, moderately reactive, highly reactive, or extremely reactive. With that classification, then that's going to impact upon the footing design. Typically, if any of you have poured through a residential building contract before, so your standard form contracts often include something to the effect of the footing design assumes a Class M soil, and then it'll be, okay, footing's $12,000, but then that's assuming a Class M soil, which there's not a great deal of in Adelaide. A lot of it, it's sort of you're highly reactive. So then what ends up happening is the extra cost of footings comes through as a variation to contract on top. Unless you've got some bore logs done beforehand and you know what classification your soil is going to be. So this is your typical bore log for there. Can anybody tell me what sort of information they get from that and what they can see from that? How many boreholes have we got happening?
6. No, 3.
3. Yep. I'll back 3 on that. Yeah. So how many horizons of soil have we got?
6.
Well, essentially we've got 6 different discernible horizons of soil there, but not expressed in all of the boreholes. So borehole 1 shows some of horizon A, some of horizon B2, B3, and B4. So hang on, 1, 2, 3, 4, 5, 6. Yeah, you've got 6 horizons there. And so borehole 1 displays 4 of those horizons, but it doesn't have any B and B1. Borehole 2 is missing some B1 and B2. Borehole 3 is just missing some horizon B2. So that looking at that, that gives us essentially a vertical. You can picture the soil. Well, some people can picture the soil from that information. So we've got, say, a site. Let's give it a little bit of slope like that. So hole number 1, and all of that horizon A, that's going to be the humus layer on top. That's going to be that good growing soil, the sort of stuff you're going to carve away for where you build your house. You want to take that away and bring in some fill, but keep it on your site because it's good for the gardens. So that 400 mil, 350 mil is our top layer, and that's expressed in every borehole. So we've got that humus content happening in that first horizon. So then our borehole 1, BH1 happening here like that, doesn't have any of horizon B and B1, so they're hardly happening. And then horizon B2 and then horizon B3 we've got happening there. But then our hole number 2 has got a bit of B1 happening here, so BH1. We've got some B1 horizon happening there. None of, B horizon, none of B1, none of B2, and we've got B3, B4. So that, as you look at this table, you see the picture of those horizons building up. And then you can look in this and get a picture of the materials happening in those horizons. So you go, all right, horizon A, that's our humus layer, that's silted clay, silt, dark grey, low plasticity. So it's a sort of greyish clay. So maybe it's not all that fantastic for growing stuff in. Then underneath that, silty clay, dark grey, high plasticity. So very malleable clay, whereas this stuff, harder, more prismatic stuff. Then black clay underneath that, very high plasticity. And then we've got some bits of variably weathered siltstone, pockets of variably weathered siltstone mixed in with clay. Because we hit some of that weathered siltstone, in sections like down only 400 mil deep, in this case 1 metre deep and 1500 deep, our Y values at the bottom here are not huge. So this is typically a lot of the information that's going to dictate what your footings are the Y values. That shows you how reactive the soil is. So a Y value of 54, 55, and 65, that's not very high. That is, actually, I can't think of where you draw the line in your classifications, but that's not too bad. It gets really problematic when you start getting Y values over 100, but your sort of 70 to 100 or so is still your highly reactive. So, but that's sitting down less than that. So it's not very reactive site. And not a great deal of differential reactivity either, which is a good thing. If we had, Y values of 30, 30, 80, that would certainly be far more problematic, because then we'd have one area which is going to be reactive, the other areas aren't going to be reactive. If it's subjected to the same amount of moisture, you get a lot of differential movement. You got more shear forces happening on your building. So different types of concrete slab footings, slab on ground. So this is our slab on ground here, and this is a car park, right? Shopping centre, whatever. That's essentially a pier and slab system. And that's what we've got in this building predominantly. This building's a mash of construction types and forms because it's been retrofitted from being a factory to being an educational building. But here we've got big concrete columns in this scenario. Basically, they're piers, right? So concrete columns, and then suspended slabs through in between those. So that's our pier and slab. You could do that on the site, Second Valley site, if you wish. You can go slab on ground. Okay, requires a little bit of cutting or some cutting and filling. But then you go, all right, well, pier and slab, elevate it slightly. That might be the go. Pier and beam. So these are your beams, and that's your piers. So typically that's used for bridge construction, things like that. But that sort of technology can be used for residential dwellings as well. A waffle pod slab. If you were to dig underneath a waffle pod slab and have a look at it from underneath, this is what it would look like. Is everybody familiar with waffle pod slabs? Yes?
I remember from last year.
Yeah, all right. You guys familiar with waffle pod slabs? So, waffle pod slabs, I think there's some. Actually, I'll get into those a little bit.
Like the styrofoam kind of, it's like esky, you kind of fill over the top of it.
Exactly. Yeah. So it's the big styrofoam box, and you just build it on a flat site. So you don't do any excavation for beams. You just level out your site like this floor. You set your styrofoam boxes out. You do your edge form work. Put the steel bars in, and then you pour the concrete over the top. Also, grillage raft. That's different from our standard raft in that those edge beams are really deep, typically like about 1200 mil deep. So we lost our soil map, but in our shocking areas of soil, Newton, Gillis Plains, etc., that's where you use things like grillage raft slabs, because you make your external beams really deep to take those forces. And strip footings, so that's an older form of construction that you'd use in a not very reactive site. The slab on ground, typically referred to as a raft slab. So yeah, stiffened raft is typically what we deal with. Has edge beams and internal beams or integral beams. Basically, the way we go about that is clear the site, and you bring in fill, compact the fill in 150 mil layers, and then dig in trenches. This is a particularly neat looking setup for a slab. So what they've done there, they've got some relatively stable soil underneath that, but then they've brought in dolomite, crusher dust, wet that down, compacted it before doing their excavation, and then when they've done the excavation, they've done some very nice, neat batters on the side. That's a very good looking slab. That is important because we contrast that with this excavation here, which is really quite rough, a lot of undulation going on there, and the edges of our beams falling away. We're going to have to order more concrete for that one. Because this one we can look at that and go, all right, well it was built, it was excavated in accordance with the plans. There's not much variance to that. We can be very confident about the amount of concrete we need. That one we're going to go, are we going to add, an extra 10%, 15% concrete to our order to cater for all those bits, those chunks, those extra chunks that have been dug out. And so you pay $300 a cube for your concrete or thereabouts. Although I was talking to a guy who's building a bit more of a crazy sort of place in the hills. He spent $600 a cube on his concrete. So high compressive strength concrete to be able to do certain things. But for your standard N20 grade concrete, so $300 a cube or so. So you're going to have to be spending more on your concrete, but also you have to do something with your soil as well. When you excavate, now I think I'll try to remember how much this guy told me he excavated his footings and had to find a place for. I think it was, I think he said it was 50 cubic meters he dug out. Yeah, that would be right. Yeah, 50 cubic meters he dug out from a site and had to put it somewhere. Couldn't put it on his site, small site. You think 50 cubic meters, right? What's that going to weigh? It's got to weigh like a shade under 100 ton. So 90 ton of soil or so. That's a lot of tippers. So 20 ton in each. So that's a lot of loads. You've got to pay for that to be transported somewhere. You've got to find a site close to where you're doing your excavation that wants to take your fill as well. So that's another reason why you want your footings to be accurate and to be neatly formed. Also very important is the lagging around pipes. All of your pipes that pass horizontally through your concrete beams have to be lagged. And if it's in a highly reactive site, they have to be lagged with 2 layers of lagging material. That's a spongy rubber that ensures that when that concrete sets around that pipe and goes off, if that concrete slab moves around, that it's not going to snap the pipe at all. There's that sponginess of that rubber to take up that movement to allow that movement. Because what you really don't want happening is certainly what you don't want happening is snapping of pipes inside, like underneath your slab. That's probably worst case scenario, which you can get. So we've got some beams happening here. This slab's going to be moving. That pipe is in that soil, going between those 2 things. You may end up with having forces transferred and cracking pipes underneath your slab if there's a lot of reactivity and you don't have any lagging. But also you get snapping of pipes right at the edge of your concrete as well, without that spongy lagging. Also, another thing we can see, well, I'm very happy with having a look at this photo. Can anybody else see what I think is a good idea of that photograph?
Use foam to protect it.
Oh yeah, well the lagging, yeah. So that's the lagging around the pipes, yeah, to protect it. But something else, it's a great idea.
It's raised higher than the ground.
So they've extended those pipes. So they're going to be taller than what you need, and you chop them off later. Like, you know, a couple bucks here doesn't really matter. It's more important that you have more pipe that you can chop back rather than not enough pipe that you have to join. Something else is good. It's good as well. Yeah. They've put caps on top of the pipes. What was that? Yeah. That's important. Well, that's incredibly important when it comes to the concrete pour, because you've got concrete going everywhere. The place you don't want it going is inside your pipes. You've got to cap your pipes. You've got to seal them off as well. After you've installed the first 6 plumbing, then you get your vapor-proof membrane down, and you lap the joins and tape them. So lap them 200 millimeters and tape them. And then following that, you fix in your reinforcing bar. So here's a slab that's got the plastic membrane down, and they've started on fixing in the reinforcing for that. So fixed into trenches, tied into a cage, and lowered into the trenches. So I guess you guys probably would have seen some of the reinforcing and whatnot going in with all this work near Tonsley as you enter. Same sort of principles, really. You'll see a lot of reinforcing cages and whatnot in that scenario. That's exactly the same sort of thing that we've got happening here. We've got them set into cages with ligatures to ensure that those bars stay in the right place. And then plastic chairs to ensure that our slab mesh sits at the right height above our vapor-proof membrane as well. We want 25 mm coverage to our slab mesh on the inside of the house, and at least 40 millimeters of coverage of concrete to our steel beams, our steel rods to the outside. So that means if that's our concrete footing here, our steel inside our concrete, that's 40 millimeters away from the edge to ensure that we don't get that steel rusting. And we also have to think about termite protection. So termite protection can happen early on by spraying down a site, or you can do things that are a little bit more environmentally friendly, like Termimesh, which is mesh, a stainless steel mesh that gets installed around pipes to help close up that gap that happens when concrete shrinks away from a pipe. So when you place concrete, it goes off, it loses moisture. That means that the concrete actually shrinks slightly. As it shrinks away from our pipes, we get a gap happening in there. Also, you can use Termi-Mesh at the perimeter of your building as well for sealing up sections, but typically that's not required. Just around your pipes. But you can also use a termiticide impregnated vapor-proof membrane as well, which is 2 layers of membrane with a layer inside that's got termiticide in it as well. So here's some pictures of slabs, slabs to be, with the vapor-proof membrane down and the reinforcing going in. So these bits here are our ligatures. Those ligatures form the shape of the cages. Those ligatures are tied to our bars with tie wire, and we want to ensure our bars are in the right place to take that tensile strength, or to provide the tensile strength within the beams. This looks like a relatively reactive, a slab for a fairly reactive site. We've got very deep edge beams. We've got our we've got 3 bars at the top of that internal beam, and they're of 16mm thickness as well. Some more photos of that site. So we can see lagged pipes as they go through the beams. It's very important. We can see the various different types of pipes there, all taped off at the top once again as well, to ensure we don't get any concrete down inside there. And yeah, plenty of length, plenty of distance on the top of those pipes. Cutting off. The formwork has to be placed very well and staked securely, because what we don't want happening is formwork to collapse and to allow concrete to spill out when we're placing the concrete. It can be quite a catastrophe because we will order, days or weeks in advance that concrete. We'll go, right, we need, 20 cubes of concrete. That's the amount we need. If our formwork collapses, we lose concrete out onto the ground. Well, certainly we don't want to be putting that, having the hassle of reinstating formwork with the weight of concrete behind it and so on. Very, very messy job, I imagine. But also, then you get wastage of concrete, and you're going to be short. You're going to have to order some more concrete quickly, which is not a good thing. You want your concrete pour to go very well. And so part of that is that the formwork is placed correctly and staked securely. We also have other bits of formwork just in forms of just pieces of timber to create set downs and whatnot. Does everybody know what a set down is and what a set down is used for? I'll see if maybe the next picture shows some set downs. So this shows a set down. That's a set down there for a bathroom. We have a set down for a bathroom because we want to ensure that if something happens with water, that water will not flow out anywhere into the rest of the building, but it will go down into the floor trap. It's not always possible to have a floor trap. In some houses with a suspended timber floor, suspended steel floor, etc., you do just platform flooring straight over the top of that. You don't have a floor trap because you can't provide any slope to that floor trap. In that scenario, you have overflow protection on your bath, overflow protection on your basin, etc., which is just a small little hole that if you were to plug up your basin and turn the tap on, that water, instead of spilling out onto the floor, is going to go into overflow protection, which is going to go into the pipe for your basin or for your bath or whatever, or laundry tub. This scenario, they've got a floor trap happening here, which means that if their toilet blocks up or something and just keeps running, that water is going to go into the floor trap. It's not going to go out into the lounge room or so. It's not going to damage wall linings. So your wall linings in your bathroom, they have to be water resistant because, or moisture resistant because they're exposed to moisture all the time. But if you get water soaking into your wall linings anywhere else in the house, that's a big problem because those wall linings swell up, they have to be removed, they grow mold, etc. And if it's happening over a prolonged period, you can also get timber rotting as well. And this place here also has a set down for the shower as well. I'll go back to where we were. So you use timber to create those set downs. So typically you'll pour the section with the set down first, and then get your timber boarding in place to protect that, and then pour the rest of the slab, which is going to be 30 mil higher or so. Placing the concrete, you have to provide 1 day's notice to the engineers for inspection, and also to the council. The council are wanting to inspect your footings before they get concrete poured in there. As I've said before, once it gets buried by concrete, nobody knows what's in there. They want to know what's in there before that happens. Concrete also needs to be vibrated when it goes in. If it doesn't get vibrated, it gets air pockets in there. Pockets of air make the concrete weaker. It's a point where there's no structure to that concrete. And so that vibration of the concrete happens with like this vibrating pole that just gets shoved in. So it's driven by a two-stroke motor or a motor, and it's shoved in there and vibrates all the air pockets up to the top. Various different forms for getting levels, etc. One common way is to get some pads of concrete, trowel them down with a laser level, get them all as reference points for your screeding. So you get all these reference points set out, and then you go pouring concrete in, and someone's working on the screed. So we don't have a picture of anybody working on the screed there. But as that happens, so you get your concrete. So here's some guys on the concrete, or they're on the end of the hose of the concrete pump. They're pouring concrete into those footing beams first. So that's getting down into the footing beams, and then they'll do the slab. After that, when they're doing the slab, you'll have one person. Hopefully they've got a motorised screed, which is they can stand up. It's got a motor on it, makes it vibrate. And they can pull the concrete around this. Otherwise, they'll do it by hand. They're leaning over and doing this with a big aluminium bar and chopping, etc., to move the concrete around. That gets a rough sort of level with lots of lines and so on in it. Following that, they'll use a bull float, which is a big flat steel trowel on a really long pole. So they'll do this and pull it over the concrete to smooth things out. And then following that, they'll use any sort of trowel. So the floating happens with the bull float, and then troweling can happen by hand, or typically it's going to happen by one of these, a helicopter. So it's not a helicopter flying, but helicopter trowel. So that one will typically have steel trowels on it, and you can get various different finishes. This motorised trowel here, like the ride-on one, that can get really good finishes happening on top of your concrete, because that can sit there just working all the aggregate down, flying across the top until you get these mirror finishes on your concrete. You can do the same with this. Essentially, it's going to take a really long time, because it takes a lot of working that concrete down to being perfect. And we saw this before. There's our set downs, etc. There. So curing is a process to control the loss of moisture from concrete after placement. If not cured properly, concrete will dry out too fast and produce a loss of compressive strength and poor durability. So you want to slow that moisture. So once the concrete has been put down, you can cover it with plastic sheets to slow that loss of moisture. You can spray it with water with a fine mist. What you don't want to be doing is, when concrete is still plastic, when it's still really soft, spraying it with water. However, you probably noticed on the footpaths here near the car park, anybody seen those during the day, that it's actually a rough finish. On your way out to the car, have a look at the concrete there. It's probably going to be a bit too dark to really see it, but it's really quite grippy. What they've done there is they've laid the concrete, and then when that concrete has gone off fairly well but hasn't hardened, they've got a high pressure cleaner over top of that to blast away a lot of the fine aggregates and give a rough surface to that concrete. There are other ways to provide a rough surface as well. You can use a stiff bristled broom. So you use a broom on top of the concrete. Probably everybody's seen that sort of finish, haven't they? Yep. you can use a wooden trowel. A wooden trowel, it's a different sort of effect. It gives a rough finish once again, but it's lots of tiny little peaks like this as the water sort of sucks to the timber. Other concrete finishes. So this is a concrete finish essentially. So what they've done here, and this can be interesting to look at around the tape as well. Look at these walls. It tells you, all the defects that were in that form ply when they used it. There's even a tiny little piece of form ply here, a little piece of wood, just in that. We've got something happening here and a bit of patching as a result. We've got these holes here from where that piece of form ply was nailed to something previously. So they've used recycled bits of form ply. And you can see these joints here. So that's by no means a class A finish. So you've got your various different types of finishes expected. This building's sort of been done with that sort of industrial sort of look to it. That's all part of it. So that's a form of finish. Has anybody seen off-form concrete before? Where you get timber boards that have the grain expressed in them. So you know it now. So timber boards that have a rough finish to them, use that as your formwork. Pour your concrete in there, pull the timber away, and you see the grain from the timber expressed on the concrete as well. So there's all sorts of different things you can do with your formwork to get expression of different things as well. Another thing is that concrete stamping. I'm not a great fan of it. Some people like that for their driveway. They'll stamp a stone look into their concrete. Any other concrete finishes people can think of?
Like grind it off, polish it up as well.
Yes.
Show the stones.
Yep. Yep. And yeah, so polished concrete and terrat, so basically the same sort of thing really. Where you've got aggregates and it's cut away to show that aggregate. Or you can also work your aggregate down a lot with a steel trowel, get a really glassy finish and just touch it up as well. Polish that top off so you don't have any exposed aggregate, but you've also got a very, very smooth finish. Any other sort of finishes with concrete? You can use acid for acid etching on top of concrete as well. Pebble dash. So you finish all your concrete and you throw pebbles on the top of it. It's a bit of a thing. So you'll see that in the paths at Mawson Lakes being done there. I guess you've got your various different renders and your various different finishes with your renders as well. Also with the curing, you can use a curing compound as well, which is typically what is done. So it's spraying a compound on top of the concrete to slow the moisture release. So we have this detail in there for our concrete footings. And that, that's probably, that may be a good detail for you to refer to. A little bit of funky stuff happening there with the measurements, though, in some things like, beam widths of 260 and 340. I don't know anybody who has an excavator bucket of 260 or 340. Some more details, so less common details of footings. Here we've got a detail with a top plate tied down to our concrete footing, that reinforcing carried all the way through. And of course, many different alternative types of footing systems. So our raft slab is probably our most common, but waffle pod is another structural system. So that's developed by Kookaroo engineers in South Australia. And it's large styrofoam boxes, and it relies upon these things called podlock spacers to produce the spacing at just the right width, and has little accommodations in there for carrying the bars, the reinforcing bars for that So as I said before, you set it out on a completely flat site, and then put your reinforcing bars, or you put your pod lock spaces in there, your reinforcing bars, plastic chairs with your mesh, your edge formwork, and then you're ready to go. It takes some consideration of what you're going to do around your penetrations in those waffle pods, because if you don't deal with that correctly and you get a waffle pod breaking and filling up with concrete, once again that's a fair bit of concrete there that you're going to have to get a replacement for. But overall, it's far more efficient with its use of concrete and steel. I won't go through the construction sequence too much, so we can see here, see it happening. Showed a concrete pump earlier, guys, carrying the hose around. This is probably the nicest type of concrete pump to use, where you've got a boom and it hangs over, and so nobody's dragging that pipe through formwork and pegs and anything like that. It's just hanging over, and they're pouring the concrete straight onto the slab. There we go. There's a fella here on the screed. So poor fella doesn't have a motorised screed. He has to do all that, and that is actually really hard work for anybody who's done. Has anybody done that? Screeding?
I had to do it on my mate's shed.
Yeah.
It was very big though.
Yeah, you had some abs after that.
Yeah, well, earlier.
Yeah, yeah. It's a lot of work to make this fella's job easier. This guy here, he's got a little box there operating the concrete pump, has to ensure that concrete is placed well, so there's not much screening that has to happen. I don't see anybody there, and also these guys are on their concrete rakes as well. So it's not a rake with fingers, but it's like a flat plate type thing that you can scoop the concrete around with. So that's a cross section through a waffle pod, showing the edge beam and then all the internal beams. So these beams, the size of those beams are much smaller than your typical raft slab. That's where your savings in concrete and steel happen, because it's a far more efficient use. But I can't think of what the maximum Y values for waffle pod are, but I think they're around the 90 or so. So for highly reactive sites, you can't use a waffle pod slab.
So it needs to be flat to start with, so there's a
Yeah.
lot more effort put into getting to that point.
No, less effort really. Any spot where you're putting a slab has to be flat. Unless it's a stepped slab, of course, that's far more involved, doing a stepped slab. But the vast majority of your slabs are going to be happening on a flat site. So you flatten that site, and then you excavate for the trenches. Once you've done all your excavation, you'll go back to here. It doesn't look all that flat. But that essentially it was all flat before they excavated the trenches. So the waffle pod is actually simpler, because what you've got is just that dead flat, and then you just waffle pod straight on top of that piece, that section which is flat. But it's not hard to get a site within 10mm variance like soil, even with a crusher dust that's got like a 3mm aggregate. You can screed that off. In fact, I've installed a lot of really big tanks on flat pads, and some places I've worked, there's been basically next to no variance, like 5mm from one side of the tank to the other, and these are very big tanks that will sort of take up this room size. So we build the first ring of the shell first, and go around that with a laser level to be picking things up, chopping, whatever. And and some people with the laser levels set on their bobcats, to get things just perfect. The technology is there to get things really good, really easily now. So pier and slab, suitable for reactive soils. That's where we've got piers going down into the ground, locking into a more stable substrate. So that might be more stable earth or soil, or rock, something like that. And then our slab can be suspended slightly from the ground to allow that earth to take moisture up and to swell underneath, and then and then subside without impacting on what's happening with our slab. Depth of piers depends on the depth of suitable founding material. Piers also may be under-reamed to increase the bearing area of the pier. So here's a thing I drew earlier, a bell pile. So that's an under-reamed pier, whereby you've sent an auger down there, and then there's an attachment on that auger that takes out this soil here, that increases the bearing size of that pier onto that soil, but also locks that pier into the stable substrate there as well. And so the reactive soil can do what it wants there. Also, there are a formwork sleeves that you can buy as well, that you put inside. So your auger holes, you put the sleeves inside your auger holes. They act as a formwork for bringing your concrete slightly higher than the ground, which makes a very nice formwork. But it also means there's a smooth side to the top of your pier, so that earth can swell and subside without grabbing the side of your pier and trying to move your pier along with it. So, so the process is clear the side of topsoil. Yeah, I won't go through that so much. So void formers put over top of the flat site, and your piers are cut and reamed, and then the whole thing is poured. Pier and beam, typically used for suspended timber construction, but can also be concrete beams as well. So once again, it's augered piers into the soil, and then you have some sort of some sort of pier structure on top of that. So typically these days it's going to be adjustable piers. They make a lot of sense, and they're very, so you just buy the adjustable tops and the bases, and then you get your 50mm RHS cut up to whatever length you need for that. And you fix the base into your concrete that's being poured there, and then the top bit gets fixed to your bearer also, and it's adjustable. So some more details in regards to sort of that suspended timber floor scenario with pier and beam construction. Just in regards, because we didn't touch much we didn't touch on timber floors when we went through timber earlier, but we did speak about spacings of joists, spacings of studs, etc. have to be at 600mm. Same sort of thing with our floor. Our flooring, that comes in standard sizes, 1200 by 2400 or 1800 by 900, etc. Everything in increments of 300mm. That means our floor joists have to be set out at those same increments as well. And if you have one that's not, well then that gets taken up at the end here, and then you get some wastage of your floor sheeting. But you have to have these joists lining up under where you have joints. Also, at this end, you do double joists. So where your joists, wherever your joists end, you do double joists there, because you're going to have load-bearing walls on top of that, and you also want to have some. So under your bottom plate, you won't want your bottom plate rotating. You won't want any eccentricity. So, and then you'll be fixing your flooring to those end ones there as well. And typically, this is what is done: is you've got your floor joist. Actually, well, that's not okay. That's not a really typical drawing. Sorry about that. So we've got some bearers happening here. But let's say our joists are running this way like that. You carry your flooring directly underneath your external walls there as well. Did I mention problems associated with platform flooring to you guys? I just can't remember because I've got to run a similar class. So platform flooring is really easy because you get your floor joist down and then you do your platform flooring on top. So this is platform flooring here in this building here. So we've got the floor joists down, the platform flooring goes on top of that, and then our walls are built straight on top of that. So you've got this lovely flat platform to be working on, tilting up your wall frames, fixing them down, etc. But I had a building that was tenanted by not my building. It was sort of a project I had to do some repair and reinstatement work on or assess for that. The building hadn't been looked after. There was a lot of moisture damage which happened with the chipboard flooring. What do when your chipboard flooring is carried under your wall frames? The determination on that one was end up the whole building has to go because it wasn't very well maintained for many reasons or in many aspects. But that platform flooring carried under the wall frame sort of tipped the scales of that, because you can't just take that flooring out and replace it with something easily because it's carried under all your wall frames. But that's your subfloor framing. Sort of in a nutshell, you've got your bearers, which happen on top of your piers, and then your joists, which happen on top of your bearers. And that's all determined from your timber span tables in AS 1684. So pier and beam sequence: pier holes are bored in foundation, piers may be under-reamed, place steel reinforced cages into the piers. Reinforced beams are then cast onto the piers, and void formers can be used where beams are cast above ground level, etc. But you form up, do all the formwork for casting your concrete beams. So this is, well, now what we showed there and what we have here, the details that relate to concrete bearers, to timber bearers with timber joists on top. But this is, here we have a scenario where we've got concrete beams with timber joists on top of that. So another form of construction is a grillage raft slab. So that's where we get very deep edge beams happening to help cater for highly reactive soils. Can be a 1 or 2 pour operation, so it depends on the amount of concrete you can get to site there, because when you've got very deep edge beams, you end up using a lot of concrete, is the thing. So done basically the same as any raft slab, except you've got very deep beams underneath. And then finally for strip footings. So that's where you don't have a slab integrated with your concrete footing strip. And those don't cater for reactive soils very well, because with a raft slab it's all tied together, it works like a raft. In a strip footing, all those concrete strips end up working independently, so it really only works in an area where you don't have much soil reactivity. And in this scenario here, what they're doing is they've got a concrete strip footing there, and then they've fixed their reinforcing bars into that. My guess is that's to go into core-filled concrete block construction. So you put your concrete blocks on top of that with your mortar in between your concrete blocks, and so those steel bars, they're spaced at 400mm intervals, and then so they will slot in with your holes in your concrete blocks, and then you pour concrete into those concrete blocks, and then you put other reinforcing that will lap over top of that, and then lay more blocks and fill those with concrete. So so the thing about Besser blocks or concrete blocks is that they've got these holes here, and if you do a staggered block, so this block here sits there like that, then that hole will line up with that one. So you've got these cores happening all the way through your Besser block construction, which then ends up being fantastic formwork for filling in with concrete. So it's a way of tying this wall in with your reinforcing and joining this wall into that strip footing essentially by that shared reinforcing.
What's the strength of it? Because they're building a house like that around the corner from me, and the bottom part's sunken into a sand dune.
Yeah, and that's a fantastic use of that form of technology. So you end up getting a very good retaining wall that happens from that. It all depends also on what's happening with your foot here as well. But yeah, it's very strong. So very good load bearing capacity, because basically it's reinforced concrete that is 200 mil thick or 190 mil thick. That's what you end up having. But certainly, yeah. But you also, so you can pull that footing to whatever shape you want, and then you end up having a solid concrete wall on top of that. So yeah, acts as a good load bearing wall and as a retaining wall. So yeah, you'll see it in situations like that. You'll see it for verandas. So verandas that are built out to carry a concrete slab on the veranda, that'll be core filled concrete block. I did it with a shed in a sloping site, cut away, but then concrete blocks, core filled, concrete slab on top of that as well. Same sort of, yeah, it's a good good approach for any sort of suspended slab like that. So that's our concrete footings. Now we've got an extra amount of time. Now, are there any questions in relation to any of that sort of stuff, or stuff relating to the assignment for some more things relating to footings and structures?
So when you're talking about it in your assignment,
Yes.
should you talk about the soil types and what the certain floor structure is good for?
Yeah. So you can say, yeah, this particular structure has its limitations in a reactive site, also. Yeah, certainly. Or yeah, this type of floor structure is good for a reactive site. That's definitely an important point to mention. Well, while we're on so we've got a bit extra time. I'm going to do essentially some showing of some other products or other ways. So another one is, this might be jumping ahead a little bit, because we're probably going to be using this sort of thing in our second and third project. But once again, it's another use of concrete, but where we've got pre-formed slabs, so slabs that are formed in a factory that have holes here, cores, well, those holes all the way through, where essentially where the concrete is not needed. So concrete is needed at the top and the bottom to help against compression, deflection, etc. But it's not, that strength is not needed in here. So you save on concrete and you save on weight, and those floor slabs can be craned in. You can also do precast, so other forms of precast slabs as well.
You use those for multi-story buildings, wouldn't you?
Yes, yeah. So that's a bit more. Yeah, it's a bit more for our second and third project. Box span steel beams. Should have any. I think they might have a video on this as well. Yeah, just quickly navigate this site. So this is a suspended steel flooring system. Um, so here. So just quickly go through it. It's a good way to get a bit of a quick overview of that as a floor system. Oh, want to get some volume happening here. Excuse me. Okay. Scroll up. Oh, with this one. Yeah. Oh, down the base of the video for the YouTube. Yeah. Okay.
That's where it should be.
Yes. Yeah. We can scroll up a little bit. Mm. Yeah, it's a bit odd, isn't it? Okay, what I'll do, I'm pretty sure YouTube was working before. Maybe our audio system's disabled. I hope not, because that impacts on the recording of the video. But here, go straight to the source. So box span. There we go. So for all your floor preparation, depending on your skin. So I had seen there was also well, haven't seen this Duragao flooring system. Might maybe check that out as well while we're here. But then there's another video installing of that. So, by the way, I'm not advocating any particular product. I just wanted to show you the various systems around. And, yeah. So thank you. You're going very quick install. Um, so, oh, significantly cheaper than using concrete. Um, yeah, I don't know a square meter rate, but um, yeah, yeah, yes, yeah, far less labour costs, far less site work costs as well. You still have to use some concrete, of course, for your concrete piers, but you can do a whole series of concrete piers for a house and end up requiring about 2 cubic metres of concrete as opposed to 8 to 10 you'd require for that same floor slab. Yeah, but then goes in very quickly as well. So and and also with your concrete slabs, you're paying for concrete, but you're also paying for the steel involved in that as well. So some of your cost of the flooring is offset by that. There was I have seen another video that was showing the installation of that box span stuff as well. Um, um, See if I can find it. If we can't find it, that's fine. Quickly and easily. Um, other other things that are going to be interesting. So we go. Actually, no. This one's more for second story, 2 story I was going to show you floor joist cassettes, but I won't go through that one today. We'll keep it single story residential for this project. Let's have a quick look at it's essentially a form of cladding. We use people in the truck as well. What they're doing there is that fire separating wall. That. So, so oh, yeah, going on the video there. Yeah. Let's quickly have a look back. So we're at 58 seconds there. And 2804. That's in relation to the panel display for the conservation application. That's using evil as a fire separating wall, so possibly support the second task, task 2. Yeah, I think we're going to see much the same. That. See what there is in terms of external. So yeah, once again intertenancy walls. Not really interested in heating. No, internal walling systems. Little power panel installation. There we go. Yeah. Oh, so top hat's going on the outside of the frame. Yeah, so some details. That. Anything else? Anybody's particularly interested in for having a look? Because we've got a bit extra time to go through some systems. We'll have a quick look at screw piles as well. Certainly you can. Yeah. Yeah. So yeah. depends on the height of your screw piles and the depth of your depth of reactive clay, etc. But you can bypass your reactive clay and lock into a more stable substrate. So these are screw piles with several screws, but they don't have to have screws. You can just have screws further down. So very little site disturbance goes on from that. So they can just screw into the ground as you see, and then they can be pulled out and taken away later on as well. So, well, it's like watching paint dry, so we'll move on. What's going to be good? This one is from where? Yeah, because the and so yeah, so in that is a problem for Australia. We don't grow any of those timbers um, to large, how to say, to significant quantities. So as far as I know, currently we're not doing any CLT in Australia. There was a CLT building built in Melbourne, um, but for now, I think you have to, all the CLT that you build with, you have to import into Australia because the quality of the timber we have here, the tensile strength of our pine is not suitable for doing it. But certainly it's a it's a good knowledge to understand in the future. pause it with that. So we've finished our time with this tonight. Is there anything else that anybody had an interest in that we could quickly have a look at? Also, in regards to this building, other forms of cladding. So I'll just shrink this one down. So next week we're getting on to covering masonry. To be looking at masonry, and so obviously a lot of that's got to do with veneer, but also other forms of masonry, and then cladding hot water systems after that. So what we can certainly cover in cladding systems is looking to some roof coverings as well in that if you wish. But if there's anything else, any other things you guys think of, this is a fantastic way of building that you want to share with the class. We can have a look at that now or also next week as well. Any suggestions? Keen to call them night. Okay. So thanks a lot for coming along tonight. Certainly if there's any queries or so, to let me know. But I'll be uploading this video as well.